Hi guys, in this video we will solve this problem mother vertex. So let's first understand the problem. So we'll be given a graph and we are required to find the mother vertex of that graph. Okay, so what is the mother vertex? Suppose if a graph is given to us like this 1, 2, 3, 4 and a node from 3 to 4. Okay, so a node is called as mother vertex if we start the traversal from that particular node, and if we are able to traverse all other nodes of the graph, then that node is said to be a mother vertex. Okay, so if we start the traversal from node 3, look where can we go? We can visit the node 3 and we can visit the node 4, and rest we cannot. This is a directed edge, this is a directed edge. Okay, so, and we cannot traverse any other node. Okay, so 3 is not a mother vertex since we are not able to traverse all the nodes. Okay, similarly if we try with any other node, if we try with 2, we can visit only node 2 and no other node. Okay, same case for 4 also. But if we try the traversal, if we try to traverse the graph from node 1, we'll be able to visit node 1. We can also go to 2 since there is an edge from 1 to 2, so we can visit 2. From 1 we can go to 3 also. There is direct edge from 1 to 4 also, or we can go from 1 to 3 then 3 to 4 also. So we can visit all other nodes. Okay, so 1 is a mother vertex since we are able to visit all other nodes of the graph. So we are required to find the mother vertex of a given graph. So how are we going to approach this problem? Okay, so I have taken a good test case. So how will we solve this problem? The idea to solve this problem is that we need to maintain a stack. Okay, what we will do is that we can start traversing this graph, means we can start the DFS traversal in this graph from any node of our choice. Whichever node we want, we can start the traversal. What we have to do is that in traversal, what we do, we simply visit one by one, we visit the nodes in depth. That is what we have to do. But one extra step that we have to do is that when we backtrack from a node, like from 4, now we cannot go anywhere else. So what we will do, we will simply backtrack. So before backtracking, what we have to do, we have to push this 4 element 4 into the stack. This is the extra step what we have to do. Okay, so first let's do that, and after that I will tell the remaining, means what else we are required to do with the algorithm. Okay, so first let's perform the DFS and fill this stack. Okay, so for now let's start with any random node. So what we can do is that let's start our DFS with let's suppose if we start with 1. Okay, so what will happen is that first 1 will be visited. Okay, now we'll go in depth. Okay, we go to 2, 2 is visited. Now we go to 3, 3 is visited. Now we go to 4, 4 is visited. Okay, so after that, after 4 we cannot go anywhere else. So what we will do, we will backtrack, but before backtracking, 4 will be added in the stack. Okay, now we go back to 3. From 3 we cannot go anywhere else, so we'll backtrack. So before backtracking, 3 will be added in the stack. Now we'll go back to 2. From 2 we cannot go anywhere else, so 2 will be added in the stack. Now we go back to 1. From 1 there is no other edge, so we will backtrack from 1. So before backtracking, 1 will be added in the queue. Okay, now we can start from any node. Let's suppose we start from 8. Okay, so if we start from 8, 8 will be visited. From 8 we cannot go anywhere else, so before backtracking, 8 will be added in the queue. Okay, now let's suppose we start from 7. So 7 will be visited. From 7 we can go to 5. So 5 will be visited. From 5 we cannot go anywhere else, so 5 will be added in the stack. Now from 7 we can go to 6. We'll visit 6. From 6 we cannot go anywhere else, so 6 will be added in the queue. Now we backtrack to 7. Now from 7 we cannot go anywhere else, so we will backtrack from 7, but before backtracking, 7 will be added in the stack. Okay, now first let me rub this quickly. So according to our algorithm, the top of the stack, the element which is present at the top of the stack, that is this particular element 7, top of the stack is the potential mother vertex. It is not confirm answer, but it is the potential mother vertex. That if check, we have what we have to do, we have to check if 7 is mother vertex or not. If we are getting that 7 is a mother vertex, then this is our answer, otherwise not. So what we will do is that after filling the stack, what we will do, from the top of the stack, that is from element 7, we will perform a DFS and we will check if we are able to visit all other vertex, then it is a mother vertex, else it is not a mother vertex. This is what we have to do. So it is saying that the top of the stack is the potential mother vertex. Okay, so let's try to do a DFS. If we do a DFS from 7, what will happen? We will visit 7, we can go to 1, 1 will be visited, we can go to 2, 2 will be visited, 3, 4, 8 will be visited, 6 will be visited, 5 will be visited. So 7 is the mother vertex. Okay, so this is what our algorithm is. What we will do is that we'll perform a DFS, and after performing DFS, the top of the stack element is our potential mother vertex. And what we have to do is that after performing DFS, we will simply apply one more DFS and we will check if all nodes are getting visited or not. If we are able to visit all other nodes, then top of the stack is our mother vertex, else we will return -1, that there is no other mother vertex in this particular graph. But here the question lies, why only 7 is given a chance, or why only 7 is considered? Why, if we are not able to get means we are not able to traverse the graph from 7, why we are not giving these elements a chance and we are simply returning -1? Okay, so here there is some question, like some confusion arises. So let's have a proof, like why we should only consider this as the 7 as our mother vertex. Okay, why this is correct? So what can happen is that there can be 4 cases. Like, let's divide it into 2 parts. What we will do is that this is the top of the stack and this is the rest of the stack. So there are 4 possibilities. One possibility is that both top of the stack and rest of the stack both contain some other vertex. Okay. Other possibility is that both does not contain a mother vertex. One more possibility is that top of the stack contains some other vertex and rest of the stack does not contain some other vertex. Another possibility is top of the stack does not contain a mother vertex and rest of the stack contains some mother vertex. Okay. These 4 are the only cases, and what we will do is that we'll analyze that in all of the 4 cases we are able to means get our answer by simply checking top of the stack as the mother vertex. We'll be able to get the answer in all of these 4 cases. Let's do that. Okay, so what will happen is that, suppose if top of the stack also contains mother vertex and rest of the stack also contains mother vertex, like that this element is a mother vertex and one of these elements is also a mother vertex, we don't know, but there is a mother vertex. So what will happen according to our algorithm? We will check that whether 7 is a mother vertex or not by performing a DFS. We'll check whether all nodes are visited or not. And since top of the stack contains a mother vertex, that means what? All nodes will get visited. So we'll simply return 7 as our answer, and that is correct also. So we are able to get our mother vertex in this first case. Okay. Now let's move on to the second case. What is second case? According to the second case, the top of the stack is not a mother vertex and there is no mother vertex in the rest of the stack also. So that means we should return -1 for this particular case because there is no mother vertex in the whole graph. So what will happen is that we'll perform a DFS from 7. Okay, and after performing DFS, since there is no mother vertex, top of the stack is also not a mother vertex, so we will not be able to visit all other nodes. Okay, since we will not be able to visit all other nodes, so what we will return? We will return simply -1, and we are returning correct answer in this case also. So we are handling this case also. Okay. Now third case. What is third case? Third case says that top of the stack is mother vertex and rest of the stack there is no mother vertex. So this is like a trivial case. We are proving this case only. So if top of the stack is mother vertex, then what will happen? We are also doing the same thing. We are saying top of the stack is mother vertex. We'll simply perform a DFS from top of the stack. We'll be able to visit all other nodes, and since we are able to visit all other nodes, what we will return? We will return the top of the stack. So we are able to get correct answer in this case also. Okay. Now fourth case. Fourth case is what? This is the main case. Like, this is where all the confusion lies. That it says that top of the stack is not mother vertex. Mother vertex is somewhere in the rest of the stack. Among these nodes, any one node is mother vertex, but top of the stack is not a mother vertex. Okay. So for this case can be divided into 2 more parts. Let's suppose we take let's suppose we take this node as our mother vertex. What? 3. Let's suppose 3 is the mother vertex for now. According to our assumption, the rest of the stack contains some other vertex, but top of the stack is not a mother vertex. Let's suppose 3 is the mother vertex. So if 3 is our mother vertex, then there are 2 cases. Like from 7 and 3, case 1. What is case 1? According to case 1, from 7 and 3, there is an edge. From 7 to 3, Let's suppose there is an edge, directly or indirectly there is an edge from 7 to 3. Okay, if there is an edge from 7 to 3, so let's make an edge over here. There is an edge from 7 to 3. Okay, so since 3 is a mother vertex, so what can we say? From 3 we can visit all other nodes. So if I start my traversal from 7, I will be able to visit 7. There is an edge from 7 to 3, so I will be able to visit 3, and from 3 I can visit rest of the nodes. So I will be able to visit rest of the nodes. So what is eventually happening? I am visiting all the nodes, and since I am visiting all the nodes, that means what? 7 is also a mother vertex. So in this case also, what? I am giving a correct answer. Since from 7 I am able to visit all other nodes, that means 7 is a mother vertex. So I am able to give correct answer in this case also. Okay, so we are able to give the correct answer in the fourth case also, in the case 1. But there is one more case in fourth case. Let's analyze that case also. So the first case we took that there is an edge from 7 to 3, that is top of the stack, to the element which means mother vertex in the rest of the stack. Second case says that there is not this edge is not present between 7 to 3. So there is no edge from 7 to 3. But 3 is a mother vertex. According to our assumption, in the rest of the stack there is a mother vertex, and we are saying that 3 is a mother vertex. Since 3 is a mother vertex, means we can from 3 we can visit all other nodes. So there is a direct edge or an indirect edge between 3 and 7. There is an edge, directly or indirectly there is an edge. Okay, so that is from 3 we can reach 7, because 3 is a mother vertex. So let's suppose there is an edge from 3 to 7. If there is an edge from 3 to 7, that is there is an edge from 3 to 7, but there is not an edge from 7 to 3, according to our assumption there is not an edge, then it is never possible that in after performing DFS 7 will come, 7 will appear on the top of the stack. It is not at all possible. Let's see in this example only. If we start the DFS from 7 in this particular graph, what will happen? All the nodes which are connected to 7 will be visited and will appear in the stack. Finally 7 will be printed, but there is no edge from 7 to 3. So after the DFS of 7 will be completed, then we will start the DFS of the 3. So DFS will appear before, means appear on the top of 7. Okay, but let's take second example also. If we start DFS from 3 also, then what will happen? Since 7 is connected with 3, that is means from 3 I can visit 7. So first 7 will come, then all other nodes of 3 will come, finally 3 will come. So in both the cases what we are seeing, 3 is appearing on the top of the stack, 7 is not appearing on the top of the stack. Let me tell this case again. What will happen is that, what we are assuming is that 3 is a mother vertex and there is no edge from 7 to 3. Okay, there is no edge from 7 to 3, but since 3 is a mother vertex, so there will be an edge from 3 to 7. So in that case 7 can never appear before 3 in the stack. That is what I am telling. Let's assume, let's take a dry run also. What will happen if there is an edge from 3 to 7? So there are two cases, either DFS can start from 3 or 7. So if we start from 7, there is no edge from 7 to 3. So all nodes which are connected to 7 will appear, then 7 will appear on the stack. Then we'll start from 3. When we'll start DFS from 3, so all nodes connected with 3 will come, then 3 will come on the stack. So 3 is coming on the top of 7. Okay, now let's check if we start DFS from 3. So if we start DFS from 3, what we are seeing, from 3 we can visit 7. So first 7 will come, then only 3 will come, finally 3 will come. So in both the cases we are seeing that 3 is coming on the top of the 7. So this particular case is not at all possible that there is no edge from 7 to 3 and 7 is coming before 3. So this case is not at all possible. So what we are seeing, among all the possible cases which are possible, we are able to get our answer if we are simply, if we are considering the top of the stack as our what, as our mother vertex, as our potential mother vertex. So we are able to get answer in all the possible cases. So I hope the confusion would have been clear to you guys, like why this particular option, like going with the top of the stack, is giving us correct answer in all the cases. Okay, so this was for the algorithm. So now let's move on to the coding part and let's try to code this problem. Okay, so now let's code this problem. So as discussed, we'll start with the DFS. We can start with any node, and we have to fill the stack. So the stack of integer stack. So what we will do, we'll one by one start with the nodes, and whichever nodes are unvisited, we'll call the DFS for those. Okay, so for integer I equals to 0, yes, then adjacency list dot size plus I. We will need something for visited, so let's make an unordered map. Simple bool array can also do the work, but we are going with an unordered map. Okay, what we will do, if this node is not visited, we will apply call DFS function. Let's write a function DFS void DFS. What we will need, a source node, we need a stack since we are pushing the elements in the stack only. So stack, okay, along with that we need a visited, get something, so unordered map of integer comma boolean visited. Then we need the our graph, so for that pair of integer adjacency list. Okay, so let's write this over here also. Source node will be I only, our stack will be st, visited array will be visited, and our graph will be adjacency list. So inside the DFS, what we do, visited of source node equals to true. Then for integer element in adjacency list of source, if this node is not visited earlier, then what we will do, we will call DFS on this node, that is element stack visited and adjacency list. Finally, before backtracking, we will add this element in the stack. Okay, after performing DFS, what we were claiming, that top of the stack is our if potential mother vertex. So what we will do, we will apply one more BFS. We will check if all the nodes are visited or not. For that, let's make a variable count. Let's clear the content of the visited. Okay, so what we'll do, we'll call one more DFS from the top element. Okay, we'll pass the visited array, we'll pass the graph, and we'll also pass the count. Let's write this function void dfs2 integer source, then unordered map of integer comma boolean visited, then vector of integer, then adjacency list, then integer reference count. Okay, what we will do, we will first mark the source equals to true, then we'll increment the counter, then for integer element in adjacency list of source, if this node is not visited, then what we will do, we will call the DFS2 for this node, DFS2 element visited adjacency list and count. And what we will check over here, that if count is not equal to adjacency list dot size, then what we will do, we will return -1. This was our potential mother vertex, so if this is not the answer, then we will return -1. Otherwise, what we will do, we will return stack dot top +1. Why +1? Because the nodes are numbered from 1 to n. Okay, and we have used zero based indexing, so converting into normal index. Okay, now let's try to run this code. See, is giving correct answer. Let's try to submit it. Let's see what happens. It is passing, so the solution is correct. I hope you guys would have enjoyed the video.